Perfect. You can go.
Okay, perfect. Yeah, welcome and thank you for having me here today. My name is Maximilian Fleck. I work as a research engineer and data steward at the PSL University in Paris. And me, Emilien, and Tess, we wrote a paper together about leveraging hidden space representation effectively in Bayesian optimization for experiment design through dimension-aware hyperpriors. And yeah, we were invited to give a talk about the subject today in your reading group. And yeah, it's on my behalf to do the presentation. And I think I will just start. And I'm also looking forward to the discussion afterwards. So Bayesian optimization. The main question, like actually we are facing this question because we are working with experimentalists and we're supporting them in lab to optimize their experimental design. So we are using those tools in practice. We are not purely theoretical here. And the main question we want to answer with the help of Bayesian optimization is usually how can we find the extremum of an explicitly unknown function? And for example, in our case, it's always, or in most cases, it's about maximizing the yield of an experiment. Oh, do you see my pointer?
Yes, we do see it.
Okay, perfect. To maximize this, we want to optimize the experimental conditions and materials, but we also need to optimize model hyperparameters, and I will cover this whole thing in the talk today. On the right, we see an illustration of Bayesian optimization. So what we got a hypothesis. This is usually our surrogate model and the data we already collected, plus our prior assumptions. Those and the acquisition function, this is what we're using to suggest new experiments. Through those experiments, we're creating new evidence, and we're using this newly gained evidence to modify our hypothesis. And we are repeating this so long till we get what we want or till we run out of our experimental budget. The second one should be avoided, obviously. So our scenario is basically we are facing experiments that are expensive and time-consuming, and we are facing search spaces that are combinatorially large. Like in the paper, our benchmark data sets are the Shields data sets, the Suzuki and the Buchwald-Hartwig data set. They have around, let's say, 3,000 to 4,000 samples. The Shields is a little bit smaller. And yeah, those are relatively large search spaces. In practice, there's a tendency to face even larger ones. So yeah. And what we do, we are using the capability of BO to exploit chemical structure, and we are using information from one set of reaction conditions to inform expectation for chemically related alternatives. This is basically a reformulation of the hypothesis. Now, what are the benefits of BO compared to maybe other approaches? Well, as I've already shown, we're establishing a closed loop. We are utilizing prior information we gained throughout a campaign or a study. Yeah, we utilize previous samples and batches, and in general, it is methodologically it enables us to systematically reduce and quantify our ignorance about a search space. And BO is explicitly informed about the goal of the campaign, which is quite important. So we are not just sampling a search space, but are informed about the goal and follow the goal. This is a difference to more classical, let's say, optimal experimental design methods. Now,
a very quick question regarding the last slide.
Mm-hmm.
The one before. So when you were talking about like the benchmarks, are those, for instance, data sets that experimentalists have come up with and that you use to evaluate a closed loop technique?
Exactly, yes. Like the Shields, Suzuki, and Buchwald-Hartwig, they're basically benchmarks where the full search space is sampled, so they are complete, and that's why you can use them. Yeah, for benchmarking. Okay. Yeah, exactly.
But they're not used to inform the prior, or I mean they're used in the evaluation process, but they're not used afterwards if you go to a different search space.
No, we are not trying to transfer this information.
Okay.
But it's a very good question. On a certain level, we are transferring, but more on the level of the hyperpriors, I would say.
Yeah.
In general, the transferability question regarding really the data is often does not work nicely. Let's put it like that.
So it's as a like hyperparameter optimization. You see what works on these data sets, and this is transferred to the experiments.
Exactly, yeah, to new experiments, but we're only doing it on the hyperparameter level to find generalized solutions that we can provide.
All right, thank you.
You're welcome. Yeah, and I think this slide very nicely matches the question, because what we want to provide, we want BO solutions that utilize as much prior information as possible. So what we are trying, like the first circle we saw had errors of equal size. What we want to achieve is basically to put as much hypothesis, as much prior information into our workflow, and with that help reduce the number of experiments needed, but increase or sustain the amount of created evidence, let's put it like that. So yeah, this is really what we're trying on the prior level. And throughout a BO workflow, there are lots of ways to add prior knowledge. On the right, we see a picture from the paper that illustrates, let's say, an example BO workflow, and I will now go through it stepwise. Just to give you an impression, the goal in this workflow is to maximize the reaction yield. We got only 2 dimensions. One is an additive, like we got different additives, A, B, C, D, which are molecules, and we got different temperatures. And within the search space, we want to optimize the reaction yield. So the temperature variable is a, let's say, easy one. It's a continuous variable, so we can easily represent that one numerically. Things get a little bit more complicated for molecules, because molecules, in this case, the additive, but it can also be solvent, ligand, and bases, whatever. So this can really explode depending on the problem you're facing. Here, the representation is a little bit tougher, because we need a way to represent a molecule numerically. A classical example would be to represent the molecules A, B, C, D with, for example, molecular fingerprints. And then you can imagine this column. The first column could maybe be the number of molecules, the second one the number of rings, and whatever. And what you need to do here is you need to decorrelate, because there might be some correlated dimensions and also some noisy dimensions, because not all of them are discrete, like a number of molecules. There could be also more continuous, more noisy features that with low variance, and you need to filter them out. If you don't do that, you will just propagate a ton of noise into your BO algorithm. When you got your representation of your molecule and you got your temperatures, you combine them into a search space. So in this case, because the molecules A, B, C, D are represented in 4 dimensions, you end up with a 5D search space, basically. This 5-dimensional vector is then the input for the Gaussian process. So we're using the representation of the molecule, we're not using the discrete molecules. And in this case, we got 12 combinations like this. So this full search space is 12 times 5.
I have a question regarding that. So if you, for instance, represent the molecules in like a 4-dimensional space, and if that space is continuous, you still get like 12 choices, but in a continuous space, or?
Yes, you're mapping it to a continuous latent space. Continuous is a little. If it's really continuous, depends on the type of representation you choose. Like if for example, the first column here is the number of atoms, you might debate if it's really, yeah. So
okay, so
yeah,
it's not really continuous unless you have a decoder,
exactly,
which is not the case.
Exactly.
Okay.
Exactly. But like I will have it. We will have a deeper look on that later.
Okay.
So yeah. So yeah, and with this we are basically training our surrogate model, which in most cases is a Gaussian process. We also now I lost track of the prior information, but you might have recognized the range of temperatures prior information we added, the different additives we want to check is prior information we added, and also the representation itself is prior information we added. Now on the GP level, there's additional prior information, for example, the choice of the kernel. There in chemistry, we usually just go for matern, so we won't debate this in detail in this talk. The same for the acquisition function, which is visualized down here. Usually it's log expected improvement. We also want to debate this in detail in this talk, but we got other hyperparameters, and those are the hyperparameters of the Gaussian process, or more precisely of the kernel. And those also can be yeah, they need to be set basically. For high dimensional cases, to keep those GP higher hyperparameters within the ranges you expect them to be, you're using a hyperprior, and this one encodes assumptions about the objective function. So this is an addition to the log margin and log likelihood. You're maximizing during optimizing the GP hyperpriors. You're modifying that with, let's say, an additional error term to keep it in the areas you expect it to be. After training the GP, you are using the GP to feed your acquisition function, and the acquisition function is used to suggest the next sample, the next experiment. And the Gaussian process is a probabilistic model, and this is also important for Bayesian optimization. I think I mentioned in the beginning that we also need to quantify our ignorance. So a GP not only returns a mean assumption or a mean prediction, it also returns an uncertainty prediction. As you can see here, like the mean is the blue line and the blue shadow is your uncertainty. And the combination, and both of them are basically inputs for the acquisition function. So the next experiment is suggested based on the mean prediction. In this case, we want to minimize this function, but also based on the ignorance, basically, about a certain area of the search space. And we see here that the maximum of the acquisition function is here, and this will be our next sample. Here, like another visualization of Bayesian optimization workflow, we see again, to give you like a view from another perspective, we see here again the continuous variables that can be temperature or concentration, but we also see discrete molecules that need to be featurized, and then everything is combined to the search space. Then we use this to, in combination with the samples we already could train our surrogate model, and the surrogate model serves as the basis for the acquisition function to suggest the next experiment, and then we're going back. And like, as you've learned now, basically on all levels of this process or of this framework, we can add prior assumptions. So where to start with? I think that your last question was very good, because like, yeah, how to present, because it directly points towards like how to represent molecules. This was basically also our entry point to the paper, to the project. And basically the molecule representation is basically the featurization, and as you see here, it's a way to add prior knowledge to your campaign. Now, how to represent them? There are some classical ways, most of you, I guess, might know. The easiest way to represent molecules is, I guess, one-hot encoding. The problem with one-hot encoding is that you're basically not using any prior information. So you're treating every molecule as a separate entity without using any prior information, how they're related to each other. This is a problem because you need a lot of samples, especially initials, because you need to sample every molecule in your search space, because they're not interconnected in any way. An alternative to that are fingerprints. I think I already mentioned them. For example, Mordred or RDKit. They are a mix of, and this addresses the question, they are usually a mix of continuous and discrete variables. And those variables sometimes have also like different magnitudes or are normalized in different ways and so on and so forth. So they are relatively messy. I think the approach here is, if you want to summarize it, is basically you're just like throwing all the information you can get easily about a molecule onto a vector, which also means that I think they got an overweight of graph-related features too. And this mix of continuous and discrete variables can be problematic, for example, when it comes to decorrelation. For example, PCA should only be done in continuous spaces. So using those with PCA is not a good idea. The third group that are reported in literature and in some works are found to be the best option are quantum mechanics features. The problem with quantum mechanics features is that the experimentalist needs a computer chemist to compute those features to run those quantum mechanics simulations. So this makes everything slower. They are hard to obtain, and they're also challenging to select. So you need to select the right features for your optimization problem. So there's a lot of, which introduces actually a lot of question marks throughout the campaign, because if you select the wrong features, you did everything and gained not much. So so we came up with the idea, or I think the idea is not new, but we wanted to check if it's a valid option. Can we use pre-trained molecular representations from, for example, transformer neural networks, graph neural networks, or LLMs that are, all of the three are fine-tuned on chemistry tasks, and can we use them to provide prior information for BO? So when we the general architecture is usually, well, no, the general setup is usually like you put in a smile string and you get something out of it. This something you get out of it can be quantum mechanics results from benchmark data sets, can be graph features, whatever. It's very diverse, and actually because like it's also it's diverse, you cannot use them directly, and even if they should come with comparable problems than than fingerprints, because they're just not comparable with each other. So instead, we are using hidden space features. They're more powerful than classical fingerprints because the neural networks that were trained usually have seen more information during training than you can obtain just from a graph. Then they're easier to obtain than quantum mechanics features, and they got nice mathematical properties. Actually, the last one was the one that pushed us towards it. And yeah, here's the visualization. We're basically just cutting the neural network and are using the outputs of a hidden space. And those hidden space features, they should be unique for every molecule. So when you input a molecule A and a molecule B, you should not only have different training outputs, you should also have differing hidden spaces. And this really allows us to map discrete molecular search spaces to continuous spaces, like to those latent spaces are continuous, especially when we assume that those models are trained with regularization and everything. Furthermore, they are interconnected, so their magnitudes are meaningful relative to each other. I tried to make this visible with the colors. When we look at the outputs of the neural network, you can say the feature 1 of molecule A is more darker yellow than feature 1 of molecule B. But you cannot relate the yellow to the blue, whereas this is kind of included. So you can also relate feature 1 of molecule A to 2 of molecule A and so on.
Okay, just wait 1 second until I manage to properly share. Yes, I think now you see the screen again,
Yes,
right?
it's perfect.
So yeah, as just again 1 second. Okay, really sorry about that again. But okay, let me now just continue. So yeah, as Maximilian explained before he disconnected, so what we tried to do in our work was to compare like different of these hidden space featurizations and to see how well they actually perform in Bayesian optimization. And so specifically what we looked at were Chameleon, which is a graph neural network pre-trained on predicting Morse descriptors. And so, I mean, the entire model puts out the Morse descriptors, but we just take the hidden space featurization from there. Then we also looked at ChemBerta, which is a transformer model that has been fine-tuned on chemistry tasks. It also has the hidden space there also has quite a lot of dimensions, so 770 in total. And then we have T5 Basechem, which is basically a large language model fine-tuned on chemistry, and its dimensionality is actually similar to what we have in ChemBerta.
A very naive question. So,
Yeah.
for instance, the GNN that was trained on Morse descriptors, I assume Morse descriptors are like you give a spice representation as input, gives you a vector. What's the intuition behind training a GNN for that? Because can't like the algorithm already gives you this information?
Yeah. So I mean, so first of all, Morse descriptors take you a little bit more time than passing through a graph neural network. But what is particular, like the real reason why this Chameleon was developed was basically to initialize ChemProp, like the regular graph neural network developed by the Green Group and Connor Coley that operates on SMILES to initialize that graph neural network with more sensible parameters than just random initialization.
Okay, so it's like a pre-training for other tasks.
Yes, exactly. And so that's what they typically apply this graph neural network to, basically for prediction tasks related to medicinal chemistry and so forth, where they then are able to show that if you use this Chameleon pre-training, that you actually get much better performance and much more data efficiency.
Okay, thank you.
So yeah, so the dimensionality that was indicated on the previous slide, that is the dimensionality that you get when you pass one molecular option through your through those networks, and you take the hidden space. But imagine that you are not just playing with the additive, but also with the solvent, the ligand, the base, and so on. Then you can have multiple options concatenated next to one another. And if each of those options has 700 or 2000 dimensions, you very quickly get a complete explosion of the search space. And so that brings us to the problem of high-dimensional BO, and specifically how we deal with these explosions in dimensionality. And so just to give you an idea that this is actually a really relevant problem here for our study, we looked here at the different data sets, the benchmarking data sets that we considered, and we applied the 3 different hidden space featurization approaches. And we used various decorrelation strategies. For example, applying a PCA analysis where we just try to keep as many dimensions that we need to explain 98% of the variance in the representation. And also removing just, for example, any dimension that correlates by more than 0.7, an R-squared of 0.7 with another dimension. So even with these decorrelation strategies, using our hidden space featurizations on the common benchmarking datasets, we can see that there's a huge variability in the dimensionality with the different representation approaches. And so you can easily get to several hundreds, sometimes even thousands of dimensions when you apply this threshold 0.9 approach, which is actually what is used by default in EDBO, for example. And so, yeah, this high dimensionality can actually give you huge problems then in terms of that. If you just take a fixed hyperprior and your dimensionality shifts strongly from one representation to the other, then you get a complete mismatch between length scales and dimensionality. And so this is actually shortly explained over here on this slide. So you can see here, I don't know if you see my cursor, but here you see the definition of the kernels that are applied in our Gaussian process model. And you have in the expression for R, which is the distance from a previously measured point. And so this indicates like how fast decorrelation takes place in the search space in our surrogate model. There is a dependency on this Li, and this L is the length scale of our Gaussian process. And so typically these LIs, they are they are fitted for every dimension, but you need to set an initial value in the beginning. And that's also what Maximilian was already pointing to. At the start, this initialization and how much you let this length scale modulate, that is governed by the hyperprior that you set for your Gaussian process model. And so the point is, as mentioned before, that if you have changing dimensionalities, that you easily get a mismatch between length scale and actual distances. Because if you increase the dimensionality of a representation, then on average, the distances that you would compute analytically between the individual points tends to increase. And so length scales, even though you give them a fixed numerical value, but because the dimensionality changes, the effective result of these length scales changes.
I have a question.
Yeah.
So if you go back on the previous slide, So in like the formula for R, like isn't the length scale dependent on each dimension? Like you have a length scale for each dimension.
Yes, yeah. And so the Gaussian process model will actually modulate the length scales for each individual dimension independently, just to fit the data as well as possible. But you need to put initial values there, and you also need to put some bounds in your hyperprior, and that's where the problem arises, because initially, when you don't know yet anything about your problem, about your data, then you just have to initialize by setting all the length scales at a fixed value. At least that's what is typically done in Bayesian optimization campaigns based on Gaussian processes. And so that is actually part of the reason why, with high dimensionalities, we were running into problems with our representations.
Isn't like on high dimensional space, the distance in a given dimension between, I mean, xi and the other point, is your intuition that this also grows as the dimension increases, even in?
I know, yeah. So distances along an individual dimension, they of course stay the same, but just as you add more dimensions.
Okay, so the R will increase, but the difference in a given dimension doesn't change.
Yeah. So you're just incrementing, like you're just adding additional increments. And so if you just have 10 small increments, and the total number is relatively small, but if you go to 100 small increments, then the total number becomes bigger. It's the L, you divide by the Li, which in the beginning of your campaign, when you initialize, that one will be fixed at one value for all i's. And so in the beginning, you can really mess up your campaign before you even started.
Okay.
And so that's sort of what we wanted to demonstrate with these plots. So what you see here are is the fitting of your Gaussian process to 3 experiments that have been run. And so what you will typically see in the textbooks or in the explanations of Bayesian optimization, you will see the light green curve where it just runs smoothly in between the 3 points. And so that's the nice behavior that you actually want when you do Gaussian process fitting. But if your length scale is not, if your length scale is mismatched to the actual distances between your data points, then you can get these problematic situations indicated by the dark green plot. So where you basically have just sharp peaks around the individual data points, and the moment you start meaningfully deviating from a previously measured point, the correlation immediately drops to 0. And so when you're in that case, there's really, I mean, you can then use this Gaussian process model to set up your acquisition function, but you're not going to do any meaningful sampling. Your campaign is dead before it even started. And the same is true on the other side. If you just have too many, if your length scale is too wide, then you will just basically end up with a Gaussian process model that is flat across the entire search space, and you are also not going to do any meaningful sampling. So yeah, that was a bit what we wanted to say here. So yeah, again, this is the common the ideal case that you want, where your length scales are nicely fit to the actual to the data and the distances in the search space. And if you have small lengths, too small, too big length scales, too small length scales, then you just get a couple of really small peaks. And it's basically constant beyond that. If your length scales are too large, then everything just becomes completely flat. Yeah, so then how we tried to tackle this, because so I've just explained that our length scales need to match with the dimensionality of the search space. But so then the question is, how do we actually achieve that? And for that, we introduced a adaptive hyperprior, which basically scales with the square root of the dimensionality. And so that ensures that most of the time we end up in the proper length scale regime, and we don't end up with the like too small length scales and too large length scales, which you inevitably end up if you would use just a fixed hyperprior, fixed length scales without taking the dimensionality into account. So yeah, that's what's mentioned here. Fixed hyperpriors will fail if you change representation. So since we expect square distances to grow on average linearly with the square root of the dimensionality, length scales also need to grow proportionally. And so that's why we need these adaptive hyperpriors. And so, yeah, what we wanted to do was to, now that we know that a hyperprior needs to scale with the square root of dimensionality, we wanted to do then a benchmarking. And so some of the existing benchmarks, the existing hyperpriors are shown on the left of this slide. And so that's what we're going to compare to. And so here you can actually see the hyperprior that we propose. So there's a square root dependency on the dimensionality of the search space, which is already what I mentioned. And then we determine the prefactor and an offset simply based on a fitting for the individual data sets that we, the benchmarking data sets that we considered. And I think there will be a plot on how we decided that in a second. So yeah, that's actually here. So how did we determine the prefactor and the offsets of our hyperprior? Well, what we actually did is we looked through all of the different representations and all of the different decorrelation strategies for our three benchmarking data sets for reaction yield prediction. And we made a plot of length scale versus dimensionality. And with the color, we indicate the performance that is obtained by these individual combinations of length scales and dimensionality. And so what you observe is that when you go to a mismatch of dimensionality and length scale, so when you either go to the upper right, to the upper left corner or the bottom right corner, there you start seeing blue dots or more blue shaded dots, which indicate that the performance of our Bayesian optimization campaign is less good. We reach an optimum yield much slower, and you actually see a region that follows the approximately the diagonal in this plot where most of the red dots are concentrated. And so that's actually validation of the theoretical argument that we were making, that if you want good performance in a Bayesian optimization campaign, that your initialization of the length scales and your hyperprior, that there should be this dependence on the square root of d, because if the length scale is proportional to the square root of d, then you maximize performance.
Just one question regarding that.
Yeah.
It looks like in this plot, in both cases, having a small dimension is usually more useful overall, as in like the performance seems to be better. I mean, maybe I'm misreading it, but for instance, yeah, the one on the right, like the darker red, I mean, it's like around 140, and the one on the left, like you usually get consistent good performance around this dimension, as opposed to increasing the dimension, where like you get, I guess, diminishing returns. Or
yes, I mean at some point you start indeed seeing that like the shade of red becomes a little bit less pronounced on the upper right corner, but the main effect certainly is the mismatch, because if you go down too much, or if you would go up too much, that's not really shown on this plot because there are fewer examples, but there you see that you really get into the blue region. And actually, I mean, the reason why we see one of the darkest red spots at somewhat lower dimensionalities may actually have to do with the specific representations, and some of these representations being better than other, which I will come back to in a second.
I'm sorry, here when you play with the dimensionality, it's still for the same method, or it's like for different kinds of methods that yield representations?
Yeah, so we basically just tried all our different representations, one hot encoding Mordred, and then the three hidden space featurization methods that I talked about. So Chameleon, Camberta, and T5 Basecam, so the large language model. We took all of these approaches, and then we fit all of them together in this plot with the different decorrelation methods, and that gives us this nice distribution.
Okay, makes sense.
And so, yeah, so basically what we then tried to do to get this prefactor and the offset was just to look at these distributions and just draw basically a line through them, and that gave us the numerical values that we used. Max, do you want to discuss the results and discussion, or do you want me to continue? We cannot hear you.
The mic.
You're still muted.
Sorry. Sorry. Before that, I have a note for the last two figures. No, the page, I think, 38. With regard to the question you discussed.
Okay.
Here you observe that it seems that the low dimensionality is good for Bayesian optimization, but actually it's not. What we see here, what we show here, these results, they are generated with default hyperpriors that are not well designed for a high dimensional bill. So you can imagine that if you go to the right side, you have a high dimensionality, then your default hyperprior, they are not working. So that's why the right side is always blue.
Okay, I see. So the point is that, I mean, other than the fact that there are good points in low dimensionality, there is also like, this only shows optimizing the length scale, but there are other parameters that are more optimized for higher dimensions that are not measured here.
we are using, well, to make this plot, we are not using our own adaptive hyperprior. We are using the default things that is employed in practice. They are not well designed for high dimensionality. So, but you can imagine that if we, like for the upper right corner, we use a default hyperprior that is manipulated by ourselves, that has a intentionally large initial length scale. So that's why it can do pretty well in this case. But if you go down, we are using other hyperpriors that are, for example, the baby adaptive, the adaptive hyperprior in baby workflow, that is not well designed for a high dimensional case. So you get a very blue point. So that's why it looks low dimensionality is good, but actually that is not the conclusion.
Okay.
Yeah. So it's. I mean, there is the further modulation of the specific hyperprior and the specific hidden space featurization, which causes some fluctuations. But overall, the trend that if there's a if you go really out of this diagonal, you end up in blue regions. That is, I think, the main takeaway from these plots.
Makes sense. Thank you for the clarification.
Okay, so and then just to actually show then what happens. So in these kind of heat maps, we're just showing on the x-axis the different representations that we tried out. So one hot mortared, and then the three hidden space featurizations that Max talked about in the beginning. And then on the y-axis, you have all of the different hyperpriors. So adaptive hours, that is the one that we worked on, that we propose. And then the other ones, they either come from existing packages, or they they come from other sources in the literature. So, for example, this SBO hyperprior, so the one right above adaptive hours, that one is a hyperprior that comes from traditional, that comes actually from the BO literature applied to data science. And so this was not specifically fitted or targeted or tuned to chemistry tasks. And so this one, for example, even though it is technically an adaptive prior, it performs badly across the board. We have some priors that perform reasonably well, such as ADBO Mordred, but on average, our adaptive our proposed hyperprior, the one at the bottom, across the different cases, it strikes the best balance. It's not always strictly the best, but it tends to give you good results across the board. And actually, we have other plots where this comes out a little bit more clearly. Yeah, so for example, already this one, you see it much better, because this is actually the speed at which we find the maximum in the in the Bayesian optimization campaign that's shown here in the B plot, and there we reach a maximum much faster on average with adaptive hours, even though the numerical values are not that distinct. So let's actually just show what this practically buys you, because I think that's the most important. These tables that I've just shown, yeah, like you see red and blue, but it's maybe not entirely clear how this is going to practically evaluate, to practically affect your optimization campaign. So here you see some examples of hypothetical optimization campaigns for one of the benchmarking data sets that we looked at. I think this is the Shields data set. And so if you would just use default settings from Baby, which is the standard approach that is often used by experimentalists in chemistry, you end up with the blue curve. So one hot and Baby adaptive, that's basically this setting. And so what you see is that you need a lot of experiments to get beyond 80% yield, and you basically never get beyond 85, 90%. If you compare that to T5 Basecam and our adaptive hyperprior, then you see that you reach a maximum much faster. So we climb much faster in the beginning. Already after 10 experiments, 15 experiments, we are we've encountered yields above 95%, and we reach essentially 100% after 30 or 40 experiments. So that's just to show that, I mean, the practical difference is quite big, and we see this across the board, where we typically need half the budget or even less compared to default approaches that were out in the literature to reach an optimum compared to the new combination of hidden space featurizations and adaptive hyperpriors that we are proposing. Yeah, so there's a bunch of plots just illustrating that what you can, I mean, sometimes the difference is less pronounced, especially when we make reasonable combinations to show together. But what you see is that consistently our T5 Basecam large language model derived representation in combination with an adaptive hyperprior performs the best. And so, yeah, that brings us to the end of this presentation. So what I think is important to take away is that if you want to do Bayesian optimization and you want to compare different hidden space featurizations, you have to look at your hyperpriors. Because a lot of the discussions that you will see about, oh, this hidden space featurization might work, or this one is not working so well in this case, a lot of it can probably, or almost entirely, it can be attributed to a mismatch in length scales from the hyperprior, which is something that a lot of people have overlooked in the past, or were just not aware of. Yeah, so I think actually the main takeaway is that we would advise experimentalists to really start exploiting these hidden space featurizations, and particularly this T5 Basecam seems to work really well in combination with our hyperprior. And actually it works so well that we've also been in touch with the company Merck, who put out the Baby software. And so we've actually contributed now this adaptive hyperprior approach to their repository. And so that also makes it now very easy to use it yourself if you want to give it a try. So yeah, and then this part I really want to hand over to Maximilian if he's still there. If not, I'm going to just skip this.
I
Max,
think he's trying to make his mic. He's trying to make his mic.
You're still
work.
muted. Oh yeah, I think there are just really logistical problems that we do not seem to get over. So yeah, I mean, it's been a bit of a chaotic presentation because of this. So thanks for everyone who stuck through till the end. I do hope that our main message has come through, namely that hidden space featurizations can really work. And it just requires you to set good hyperpriors. It's actually a relatively simple solution, and we actually propose a strategy that we think is broadly applicable. And we really want to encourage experimentalists who oftentimes struggle with getting good results with Bayesian optimization to try out this T5 Basecamp plus adaptive hyperprior combination. Thank you very much for your attention.
Thank you. Thanks to all three of you. I think it was a great presentation. It was very clear. And yeah, thanks for catching up and saving the presentation as well. It was, I think it was like very smooth anyways. So I have, I mean, for people in the who are still there, you can still ask your questions in the Q&A. I have a few questions. First of all, congrats for having your work included in the package for Bayesian optimization. I think that's really great. Maybe a more intuition-based question is like, when you were using high hidden space features in high dimension, like were you observing that it doesn't work, and like how did you go from it doesn't work for Bayesian optimization to it's a problem of the hyperprior and not the hidden space features themselves?
So I think, I mean, it's a common frustration, like especially when you use default methods such as one-hot encoding in combination with the default hyperpriors in Baby, that you oftentimes collapse too early on. You basically don't do exploration anymore. You just you just do an initialization, and then it picks the best performing option basically at that point, and it just keeps proposing slight variations of that. And that is actually presumably a reflection of this mismatch already that we were observing, or that we pointed to with some graphs in the beginning. Specifically in this work, how we decided that we really needed to take a closer look at the hyperprior. It was primarily intuition from Max's side that this was a real problem that we needed to address. Controlling the speed at which you get decorrelation is of crucial importance across your search space.
Oh, I think you can hear me now, or?
Yes, we can. Oh, great.
I also tested it on neural networks in the beginning, and that I performed very nicely. So it was surprising that it didn't work for GPs. And I knew from experience that if GPs don't work when they should work, usually the problem is not the GP, but the person in front of the computer, which in that case was I. But okay, as today.
All right, and another maybe high-level question is, I'm not very familiar with doing Bayesian optimization or like experimentation, but is Bayesian optimization actually currently the best method for searching through space for experiments, or does it depend on the problem setting and other things?
So I think that it provides a very appealing and grounded approach to balance exploration and exploitation, and that's why people like it so much for especially reaction optimization, and especially when you work with continuous variables, it is commonly used. Of course, if you want to do, for example, active learning across molecular options, it was not used like that in the past, exactly because you often had mismatches and because you had high dimensions and your Gaussian processes could not properly deal with that. So I think that a lot of the comparisons that have happened when you are considering, for example, hundreds of chemical options, there in the past, Gaussian processes would not come out in a very favorable light. But some of these cases can probably be revisited now if you just use a good hyperprior, because the comparison may not have been fair before. But yeah, it's especially when you're dealing with a limited number of continuous variables, which is often what you have in experimental setups, and just a handful of chemical options, then Bayesian optimization has always had a reasonably good reputation. And it's actually like, so in the benchmarking data sets that we considered here, those are actually examples of that, where you typically have just 5 or something additives, for example, or solvents. But so yeah, and even there we are able to demonstrate that we already get major gains with our approach. So yeah.
Right, and one last question. So it seems that, I mean, the findings of your work, I feel like it's not only chemistry related, right? You can use it on any kinds of descriptors for any kind of modality, and like this is something that if you're fitting Gaussian processes, you would need to do, right? Have hyperpriors that depend on dimension.
Yeah, there's actually some discussion in the BO literature about that. And before you use a general purpose prior, you should think about maybe you should test it. Like in the BO literature, like we also saw that those general purpose priors, for example, the one that is the default in Blowtorch was outperformed by AdBo+, for example. So there seems to be a certain possibility basically to build domain-specific priors that outperform those general purpose solutions. So yes, you can use them, and it would be also cool to test our prior outside chemistry. We hope that the baby developers will run their test framework with it at one point. But you should test it, and you should be aware that the more you generalize, the worse your single campaign result potentially gets. So it's a trade-off, basically.
Yeah, because and I just want to add one more thought to that. Is that yeah? So it's exactly what we did. Like we focused narrowly on reaction yield optimization here, and so our offsets and our prefactor, like the 0.4 and this 4 that we derived from this plot that I showed 10 slides or something ago. That's really the fine-tuning on reaction yield data sets. And so using a general purpose adaptive hyperprior, as Maximilian mentioned, that was one of the entries in some of the heat maps that I showed, like the one that was completely blue. It's just because the prefactor and the offset there are just not well fine-tuned for chemistry tasks. So we think that for given groups of tasks, you probably need to come up with slightly adapted hyperpriors, but the general strategy is broadly valid. It's just that in chemistry, with representation of molecules, it's such a pertinent problem to think about that you really have no way around it, I would say.
All right.
Yeah,
thank you so much for answering my questions. I think there are, yeah, and yeah, I don't think there's any more questions in the chat. I don't know if you want to highlight some other things, but it was great.
Okay, yeah, so yeah, then there's the thank you again for hosting us, and apologies again for the.
No worries, it was great.
But yeah, I mean, if you want to have a full read, the paper is out as a preprint, and hopefully it will be accepted in a couple of weeks also in chemistry journal. So then you can give it a full details look. Thank you.
See you all.
All right.
Have a
Bye.
nice day.
Thanks a lot.
Thank you.
Good night.
Sorry.